talk about generalizations of the isoperimetric inequality in higher codimensions and their applications. So let me start by sharing my screen. Here's the title of my talk. And let us start with the classical isoperimetric inequality, which says that if you're given a domain omega in the Euclidean space Rn, then the n-dimensional volume of omega is bounded from above by a constant that depends only on n times the n-1 dimensional volume of the boundary of omega. To the appropriate power that makes this scaling invariant. So this is a slightly unusual form of writing down the isoperimetric inequality. Usually it's written the other direction, from right to left. We write that the volume of the boundary is bounded from below by the volume of the set, and this constant n here is such that the equality is achieved only when omega is a round ball. So we usually think of this isoperimetric inequality as saying that if you want to minimize your perimeter, then you cannot do better than picking a round ball. I'm writing it in this form because we will be interested in asking for a similar inequality in a situation where omega is not a domain in Rn, but a submanifold of higher codimension. So in higher codimension, we can ask for an inequality that looks kind of like this. But when we start with some k-dimensional submanifold M, k is now smaller than n-1. Okay, so the first thing that we notice is that M admits infinitely many different fillings, unlike boundary of an open set in Rn. So here we could have a filling like that. We could have a different filling with many fingers. And of course, these different fillings can have arbitrarily large k+1 dimensional volume. So it doesn't really make sense to ask for an inequality that controls the volume of any filling in terms of the volume of the boundary. However, we can ask about the best, the smallest filling. And then there's indeed a very important inequality of this kind that was proven by Feder and Fleming in the 60s. In fact, it comes out of their deformation theorem, which they proved with a slightly different purpose, but as a byproduct of their deformation theorem, we have this isoperimetric inequality. That if you have a k-dimensional submanifold in Rn, then it exists in N. There's a k+1 dimensional manifold with boundary N. Boundary of M is equal to M, and the k+1 dimensional volume of M is controlled in terms of the k-dimensional volume of M. Right, so in this form, it does look like the previous isoperimetric inequality, the classical isoperimetric inequality we wrote about, except that here this is true for some specific nice feeling. So we claim that there exists this nice feeling, which is small. In fact, the proof of Federer-Fleming was for a much larger class of submanifolds, not just smooth submanifolds, but their singular generalizations, like Lipschitz cycles or integral currents. And the argument is a really beautiful one and very useful in many places, in many geometric arguments, that what you want to do is, given your Rn, you want to pick a grid very nice grid. But think of the lattice here, and that picture is really terrible. Let me do a better job. Just draw one sort of cell, this lattice, and then we look at our M inside here, and we pick a point inside each cube, each cell of the lattice, and deform by projection this portion of M that lies inside that cube into a lower dimensional skeleton of this grid. And the observation is that if we pick a bad point, then we can run into the problem that we have. Oops. Then we can run into the problem that we have a very large ceiling and projection obtained from this procedure. But they observe that we can use Fubini's theorem to average over all possible projections, and then by this averaging argument, we will always have a point that will have nice properties. And then if we pick the size of the grid correctly, then it will also give us an isoperimetric inequality. Right, so we start with the feeling in the just pushing everything into n-1 dimensional grid. Then we do the same thing for every n-1 dimensional phase in this grid to push it into n-2 dimensional grid. And we keep doing that. And at each step, we control how much area we are introducing by picking a nice average point. And so eventually we push everything into a k-1 dimensional grid, and then we know that we can fill it. So this is the argument of Federer and Fleming, and it has been generalized in a number of ways, and I will not mention all of the results in that direction, but only the ones that will be relevant for us. So here's some improvements. So in 1970s, Michael and Simon showed that in this inequality, you can change the constant that depends on n to a constant that depends on k. In other words, we can prove this inequality in a way that is independent of the dimension of the ambient manifold. And so the ambient manifold can be very large dimensional, but this boundary will depend on the dimension of M. Then Gromov in the 80s pushed this further, so not only the bound doesn't depend on the dimension of the ambient manifold, but in fact, we can prove this isoperimetric inequality in an infinite dimensional Banach space. So for 1980s showed that if you have a Lipschitz chain in a B, where this is a Banach space, possibly infinite dimensional, then you also have isoperimetric inequality of this kind. You can find a k+1 dimensional chain whose Hausdorff measure will be controlled in terms of the Hausdorff measure of chain Z. And then this result of Gromov was later proved in a different, simpler way by Stefan Wenger. Simple proof. It's a very nice proof, and I highly recommend reading it. It's just a 2-page proof of this result. Why is this interesting? Why would we want to, improve the dependence of the constant on the dimension from ambient dimension to the dimension of the manifold? And why would we care about generalizing this isoperimetric inequality Euclidean space to Banach space? The reason Gromov looked at this was because of the connection he observed to some important basic metric invariants of Riemannian manifolds. So let me write down what they are. So one invariant is the system of manifold M. Another invariant is the filling radius of M. And the third invariant is the Urysohn width. Let's say M-dimensional Urysohn width of manifold M. Okay, so let me define what they are. The simplest one is the system. It's just the length of shortest non-contractible closed curve loop in M. So for example, if our M is a torus, like that, then we can consider its fundamental group, and we can realize one of the generators of the fundamental group as a closed geodesic, and we can take the infimum over all curves realizing this non-trivial homotopy class, and we can find a closed geodesic which will give us the shortest non-contractible curve in our manifold. The filling radius is defined in the following way. It is the infimum over all radii R, so that there exists an isometric immersion. In fact, we want, I guess, an isometric embedding from the manifold M into some Banach space B, such that there exists a filling of M inside B. In other words, the image of M considered as a cycle bounds an n+1 chain in the R neighborhood of inside B. And here, the isometric means not in the sense of isometric when we talk about Nash embedding theorem, but actually isometric meaning that the distance in the Riemannian metric on M and the distance in the ambient Banach manifolds are equal. It's not that the restriction of the Riemannian structure on the ambient manifold gives us the same Riemannian structure. It's the actual distances that are equal. So in particular, most manifolds will not be able to embed in any finite dimensional space, but you have to embed them in an infinite dimensional space to get an isometric embedding. And finally, the Urson width is defined as the infimum over W, such that there exists a map F from M into some M-dimensional. So this is an M-dimensional polyhedral complex such that the diameters of the preimage of this map for all x is bounded by this number for all x in this polyhedral complex. So what this looks like is that your manifold can have large dimension, right? But maybe it can be mapped into a smaller dimensional polyhedral complex. Maybe somehow like that. And the fibers have small diameter. So if this M-dimensional Urson width is small, then from very far away, our manifold will look like an M-dimensional object. And so Gromov observed the following relationship between these geometric quantities, between these metric quantities, that the systole manifold M is up to a constant bounded by the filling radius of M up to an absolute constant, and filling radius in turn is bounded by Urson width of M between 1 and n minus 1. And this is true for a large class of manifolds. So let me say what they are. So if M is essential, this is a topological class of manifolds, which includes, for example, all spherical manifolds, in particular all hyperbolic manifolds, manifolds like tori, RPN, or any manifold connect some with any of those manifolds. Then we have a bound on the length of the shortest non-contractible loop in the manifold M in terms of the filling radius or the Urson width of manifold M. Furthermore, Gromov proved the following. He realized that one can use the isoperimetric inequality in the Banach space to control the filling radius and therefore control the system. So it follows from the isoperimetric inequality in Banach spaces that he proved that the filling radius of M is bounded by a constant, which depends only on the dimension of the manifold, times the volume of M to the power 1 over M. And therefore, by the previous inequality, the system is bounded by the nth root of the volume of the manifold. And then he conjectured that the similar inequality also holds for the n-1 dimensional Urson width. And that was later proved by Larry Guth. Larry Guth used isoperimetric inequality in finite but very large dimensional spaces to show that the n-1 dimensional Urson width of manifold M is controlled by a constant times the volume of M. And so that's a stronger inequality, but it also implies the systolic inequality, the bound of the systole in terms of the volume of the manifold M. So let me comment a little bit on the ideas in the proof. So Gromov's proof went by embedding manifold M into the space of L-infinity functions of M. So this is the famous Kwiatkowski embedding, which takes a point x and sends it to the function that is the distance from x. One can show using the triangle inequality that this embedding is actually an isometric embedding. And now we have that our manifold lies inside of a Banach space, and we can use the isoperimetric inequality to construct a filling of the immersion inside this Banach space L-infinity M. And furthermore, the isoperimetric inequality can be used not only to control the volume of the filling, but also how far does the filling lie from the boundary. Because if the filling has very long fingers that protrude far away from the boundary, then we can pick this point, which is far away from the boundary, and using Cohere inequality, find small intersections with the geodesic spheres from this point inside this Banach space. And then to these intersections with geodesic spheres, we can also apply the isoperimetric inequality. And playing with these two inequalities, we can cut away all of those fingers and show that, in fact, there is a filling that lies at a controlled distance from the boundary. So there is a way to update our isoperimetric inequality, which is a control on the volume of the filling, into a filling radius inequality, which is a control on how far the filling lies from the boundary. And it's in a similar spirit as the monotonicity formula for minimal surfaces. We know that if your filling is somehow close to optimal, then it shouldn't have long fingers. Now, Guth's proof for the Urson width is somehow, it begins in a way that feels like a finite dimensional version of Gromov's argument. So Larry Guth starts with fixing a very cleverly chosen covering of our manifold M by Bowles And then he defines an embedding into what he calls a rectangular nerve of this covering. So basically what's happening is that, so we map M into rectangular nerve of the covering O. So here we have a covering from 1 to n, and then we will define a product space where each size is the length of the radius of the ball bi, and we will define functions pi of x. So we have as r pi minus the distance from x to the center of the ball pi. So we have that balls pi are equal to the ball of radius ri around the point pi, and 0 if x does not lie in the ball pi. So if this is our manifold M, then we consider balls of radius, various radii, b1, b2, b3, and so on, and we define these functions which are equal to the radius when you are at the center and decay to 0 as you move away from the center. And so we define a map capital Phi, which takes a point x and maps it into an n-tuple Phi1 of x capital X, with at least one of them will be non-zero because our BIs is a covering. And so this takes our manifold M and sends it into this rectangle, capital N, dimensional rectangular space. Sorry for my terrible rectangles. And these radii are the length of the sides corresponds to the radii of these balls. Okay, so this is a very large dimensional space, but Larry observes that if you pick those balls with certain special properties and you use the isoperimetric inequality in a careful way, then you will be able to push the image of this map inductively into n-1 dimensional skeleton. So this is, let me call this Q, we call this rectangular nerve as Q. So you will be able to push this image into n-1 dimensional skeleton of Q, and you can control how much you move the points of Q. And so when you look at the pre-images of the resulting map, this will be precisely the map that gives you good control on the n-1 dimensional Gruson width. The diameters of the pre-images will be small. And the reason why you can make those make this inductive push, even though you don't have control on how many times you need to push into smaller skeleton, is precisely because you can carefully use the isoperimetric inequality in this rectangle, using isoperimetric inequality. So both of these arguments have in common that you're putting your space into some either infinite dimensional or very large dimensional space, but you're able to use the fact that your isoperimetric inequality is independent of the dimension of the ambient space to deform it into something small, to fill it or to deform it into a smaller dimensional space. Okay. Let me now talk about generalizations of this result. So Larry Goth conjectured that it should be possible to bound the Urson width with a different quantity, not volume, but a weaker quantity called Hausdorff quantum. So replace volume with Hausdorff quantum. And as a consequence, obtain a new systolic inequality, where the length of the non-contractible loop is controlled in terms of the Hausdorff quantum of the magnet. So let me define the Hausdorff quantum. So recall that the way we define Hausdorff measure of the space, volume, is by taking the lim inf as radius goes to 0 of the infimum of the sum of radii of balls in the covering. So M is contained in union balls B, P, I. And all of these RIs have radius. All of the balls have radius less or equal than R. Okay, so let's give a name to this quantity, the infimum of the sum of radii to the power of k of all balls, where the radii are at most R. Let's call it HRK. And so the Hausdorff measure is the lim inf of these HRKs, where R goes to 0. And the Hausdorff content of M is just simply forgetting about the upper bound on radii in the covering. So that's just H infinity K of M. We're allowing coverings by balls of any size and then take the sum of their radii to the power of K. So a few things to note about this quantity. So properties, Hausdorff content. First of all, the k-dimensional Hausdorff content is bounded from above, is smaller than the Hausdorff measure, the volume of space X for any metric space X. This follows immediately from the definition. Now, if X is a compact metric space, then Hausdorff content is finite. So we can take, for example, a three-dimensional manifold and measure its two-dimensional or one-dimensional Hausdorff content, and they will be finite, unlike the Hausdorff measure. If M is a connected manifold, or connected metric space, then we have that the diameter of M is bounding from above the Hausdorff content of M. So the one-dimensional Hausdorff content of M will be somewhere between the diameter and half the diameter. So M is, let's say M is n-dimensional, and then it's bounding from above the square root of the second Hausdorff content, and so on, all the way to the nth Hausdorff content to the power of n, which is greater or equal to n plus first Hausdorff content, which is just equal to 0. So another thing about Hausdorff content is that it's not a measure. So this is something not so convenient if you have a measure. If you have, for example, a disk and you construct an annulus by removing a small disk. So this is U1 and our small disk will be U2. Then it's easy to see that the Hausdorff content of U1 disjoint union U2 is not equal to the Hausdorff content of their. It's not equal to the sum of the Hausdorff contents. In fact, it's strictly smaller than the Hausdorff content of U1. Is just going to be equal to the Hausdorff content of U1. The reason why we would want to use Hausdorff content is because it ignores what's happening on the small scale. So it is very convenient to use it if you have a lot of wrinkling on a small scale. So let me give you an example. For example, we want to look at the two-dimensional Hausdorff content of a surface. And the surface looks like a torus, which is very, very thin. For a surface like this, we have that the two-dimensional Hausdorff content is very small and the area is also very small. However, what we can do is we can start adding wrinkles on a small scale to this torus. For example, we can start adding tiny but very large area hyperbolic surfaces and take a connect sum of our long torus system. So area can now be made arbitrarily large. But the two-dimensional Hausdorff content will continue to be small. So in this case, two-dimensional Hausdorff content is much smaller than the two-dimensional volume of our surface. And you can see that even though the area is very large, this object still looks sort of one-dimensional from far away. So in this respect, it does look like it should obey Larry-Goose conjecture that if your Hausdorff content is small, then you should have small Urson width. You should have small Urson width, one-dimensional. And this is indeed what we proved. Is Boris Lishak, Alexander Nabutovsky, and Eugene Rothman. We showed that, first of all, if M is a compact manifold, then the M minus one-dimensional Urson width of M is controlled by the m-dimensional Hausdorff content. Now this m is not necessarily dimension, but it's any number. So m is somewhere between 1 and dimension m. If m is equal to n, then this generalizes Guth inequality, because the Hausdorff content may be much smaller than the area, like in this example, because we are ignoring things on small scale. But if m is strictly smaller than n, then it gives us really a new geometric inequality. And as a consequence, we also get a systolic inequality. So we need a topological condition, which is a condition which somehow describes topological non-triviality in dimension m. So if m is m essential, so an example of an m essential manifold would be something like RPM cross say S4 connects some S m plus 4. So something like that. So something that has a factor here, which is m central. Then we can control the systole of m in terms of the m-dimensional Hausdorff content. And indeed, when m is equal to n, then this inequality is an improvement, because Hausdorff content is smaller than the volume. But for other values of m, we get really a new inequality, because for something like something's wrong with my pen, just a sec. Okay, it's working. For a manifold like a 2 torus cross S2, previously we didn't have any control on the size of the systole in terms of some geometric information about this manifold. And now we control it in terms of the two-dimensional Hausdorff content of this manifold. Okay, and the way we prove this result is by generalizing the isoperimetric inequality from volume to Hausdorff content. So we follow the strategy of Gromov and Guth of embedding our manifold into some Banach space and then deforming it in a controlled way using the isoperimetric inequality. So let me state the generalization of the isoperimetric inequality that we proved to get this result. Okay, so there is one way of looking at the isoperimetric inequality that allows really a vast generalization. So we can take a point of view that we are not filling a submanifold with some submanifoldless boundary, but we fix the manifoldless boundary from the beginning, and we're looking for an extension. So say we are given a k plus 1 dimensional manifoldless boundary of m is equal to m, and we are looking for a map from, and we are given a map from m to some ambient space B, some Banach manifold, for example. And so then we can state the isoperimetric inequality in the following way. So this would be a more general statement than the one that I stated before, but that can be proved using pretty much the same techniques. that there exists an extension f n into b, and extension here means that the restriction of f to the boundary of n, which is m, is equal to f, such that the k plus one dimensional volume of the image of this extension is controlled by a constant that depends only on k times the k dimensional volume of f m power of k plus one over k. And so what we'll do now is we will generalize each object here. So we will generalize n to any metric space X. The boundary of n, we will switch to any closed subset. And then we will change volume to Hausdorff content. So with these changes, we obtain the following result. Also joint work with Boris Lishak, Alex Nebutovsky, and Regina Rotman. Which is that given any number m greater than 0, Banach space B, possibly infinite dimensional, metric space X, and a closed subset Y, if f is a map from Y into B, then there exists extension so a continuous map, then there exists a continuous extension f, little f, such that the m plus one dimensional Hausdorff content of the image of capital F is controlled by a constant times m-dimensional Hausdorff content of little f of y to the appropriate power. The way we prove this result is by imitating the arguments of Wenger and also Federer-Fleming, and proving versions of these things for Hausdorff content. The main issue is that Hausdorff content is not measured, and the main problem is the absence of additivity for Hausdorff content of disjoint sets. And so we have to be careful with how we compute the Hausdorff content using different coverings. We have to pick different coverings at different moments in our proof and make sure that the overlap between both is not too large. So we have to prove things like query inequality and cone inequality for Hausdorff content, and do a induction argument similar to the one that Wenger uses in his proof of the isoperimetric inequality for volume. This inequality is very different, is very interesting because it's very general, and also another reason is that it's very interesting to try to understand the sharp constant here. There's one specific case where this constant may be very simple. It may be just equal to 1. So we conjectured in the paper that when your Banach manifold is equal to L infinity, which is just the collection of x2, so on, and the distance between xi and yi is the supreme. The differences so that in this space theorem above, let me call it theorem 2, holds with C of M just equal to 1. But we actually conjecture something weaker, that it's that there exists an inequality like this plus epsilon for every epsilon greater than 0. For every epsilon greater than 0, we can find an extension satisfying this inequality plus epsilon with constant equal to 1. And if it's true, then it would imply a nearly optimal systolic inequality, which is a long-standing conjecture. And it seems that if an inequality so simple holds, then the proof should not be terribly complicated. But it's right. So let me leave it at that. So I hope I convinced you that the various generalizations of the isoperimetric inequality lead to very interesting new results about Riemannian manifolds. There is another interesting open question related to isoperimetric inequality, which is the parametric generalizations. Parametric, isoperimetric inequalities. Instead of trying to prove the isoperimetric inequality for other quantities, not volume, but other ways of measuring size of the space, we can consider not one object, but a family of moving objects, and we can consider different ways how they could move. Problem that arises very naturally in the study of the geometry of the space of cycles is if we consider manifolds moving in, or cycles moving in the flat topology. So we have family ZT, T parameterized by X, where this family is continuous in flat topology. So flat topology means that two let's say Lipschitz submanifolds are considered close to each other if together they bound a submanifold this boundary of small area. So if you have, this is your Z1 and your Z2 has two components, then we look at submanifold is boundary of dimension smaller, of one dimension larger, and so then the flat distance between Z1 and Z2 is defined as the volume of the smallest field here, smallest volume still in tau. Boundary of tau is equal to C1 minus C2. So imagine now that we have a family of feelings with this family of cycles with this topology. Can we find a continuous family of feelings whose size is controlled in terms of the sizes of these cycles. So more specifically, given family ZT, is there a family of chains, cycles, tau t, such that the boundary of tau t is equal to ZT, and the volume of tau t is controlled by a constant times the volume of CT power of k plus 1 over k. So these are k-dimensional cycles, and these are k plus 1 dimensional chains. Then this is something that we could ask. Now, the main question here is really about this constant c. If our parameter space is p-dimensional, then it's not hard to prove an inequality of this kind where this constant c depends on p in an exponential way. So something like 10 to the power of p or 2 to the power of p comes into this bound. But one of the questions one could ask is, would it be possible to construct a family of feelings that doesn't depend on p at all? So this is just constant that depends on k, or maybe ambient dimension n, but not on the number of parameters in your family. And something like that would follow from at least in codimension 2, it seems that something like that would follow from an inequality for high codimension isoperimetric inequality of Simon Brandl that he proved not long ago. But in high codimension, it's still not clear if this is true, how one would prove that. There are various other versions of this parametric isoperimetric inequality, which have applications to min-max theory and to volumes of minimal hypersurfaces. But this would be a topic for a different talk. Thank you very much.